let's go ahead and get started. I think you may be seeing in lab and in the reading, the difficulty level is definitely starting to go up at least a little bit because, now that we have this concept of arrays that we've been working on, combined with that of loops, really it just opens up a lot more possibilities of what is possible. Um, at the end of the day, the kind of code you are writing with arrays and loops really is going to follow the same basic patterns we have in this example from last Friday, where we were looking at two-dimensional arrays and copying from one variable that was a two-dimensional array to another variable of the same size that was also a two-dimensional array. Things to keep in mind is when you define your array variables now, that's just another thing we have to think about upfront. We always have to think about the name. What's a good name for the variable? Okay, A and B are not good names, but those are two names we had to think about. We always have to think about what is the fundamental type of each of the elements of that variable now that it's an array. For now, we just say, okay, we're working with integers, that's fine. And now that we have these variables that are arrays, we really have to think about, what is the size of these array variables? What is appropriate for the type of problem I'm looking to solve? How many dimensions does it need to be? And then what is the size of the individual dimensions? Oftentimes, not always, but oftentimes once you've answered that, okay, I need a 25 by 25 array of ints. Once you have that in mind, the resulting for loops that do stuff with your arrays kind of is like directly flows or is a consequence of the choice of variables that you've picked. In the example of this array copy code, and I'll just bring it open here in Replit, it was kind of a given that we decided, well, we're going to have these two-dimensional arrays, A and B, and they're going to have one dimension be of size num rows and one dimension be of size num columns. So A and B, when we declare them, are effectively declaring 5 cross 10, 5 times 10, 50 different integers for each of those variables. Now, this terminology of rows and columns for an array only really kind of makes sense for like a two-dimensional array type. Once you have a 3 or 4 or 5 or 6 dimensional array, you really can just refer to them as dimension by dimension. The term rows and columns doesn't necessarily mean that much, but we describe them when we declare them from left to right. Those are the corresponding dimensions. And then when we subscript them, we also subscript them from left to right. So this code that initializes A is going to wind up looking very similar to this code that prints out A. And it's going to wind up looking very similar to the code that then copies an element of A to the corresponding element in B. It's not always going to be exactly this, but generally, if you have an n-dimensional array, where n in this case is 2 for 2 dimensions, you're very likely going to have an n-nested for loop for accessing each of the individual elements inside that array. Now, what you need to do with that for loop really depends on the problem, so it doesn't, it's not solved what you have to do, but generally, I have a 4-dimensional array for whatever reason. I'm probably going to have a 4-dimensional for loop to access each individual element of that array. And just like for the 1-dimensional case, if you have z elements in the array, you're going to have a for loop that goes from I equals 0, I less than z, I plus plus. And that for loop is going to give you all the valid subscripts, all the valid indices into that particular dimension in that array. Because unfortunately, for better or for worse, in C, we really don't treat these arrays as kind of built-in types in the language. They're built in terms of syntactically they're valid, but while it would be really nice to just be able to say in my code, B equals A, assign all of B to all of A, it is syntactically valid what it's trying to do. It's trying to kind of copy addresses over, but it doesn't wind up copying the values of A over into the values of B. That's not really a valid way to work with our arrays in C. We are generally going to have these loops so that we can have some part of our code that at some point is accessing every individual element of A or every individual element of B. That's not to say, and then again, once we have that, we have code that hopefully is a lot more expressive and a lot more powerful than if we had to declare, let's say, 50 variables and copy all 50 variables over. While we're still doing what I was referring to as static memory allocation or compile time sizing of these arrays, because we have these pound defines, and when we compile the program, the compiler is aware that you have 5 times 10, 50 elements in each array. It's still very static. We'd have to recompile the program if we decided we didn't want 50 anymore, that we actually wanted 500 elements in that array. But hopefully, if you write your program using this kind of style, where you don't hard code the value of 50 anywhere, or 5 it was before, anywhere in your program, and you use that pound define or a constant integer variable to keep track of that dimension, then when you decide that, yes, I actually want not 5, or for testing purposes, it's way too difficult to print out 50, I'm going to print it out with 5, I want to change it from 5 to 50, then in theory, if you allocated your arrays using that pound define, if all of your for loops are kind of scoped by that pound define and limited by that value, then that change, if you do things correctly, it's still not going to look very good here because there's a lot of things we're printing, that change should be like a one-line change. And we've gone from a code that does a 5 by 10 to now a 50 by 10 to a 50 by 100, and we've changed, essentially nothing in our program, right? We've changed just that pound defined, and we're not comparing each value manually to confirm, but it looks like it's working. It's copying all of those values over. So as always, think about what your variables need to be first, both in terms of type, name, and now basically dimensions and size of each dimension. And once you have arrays versus having just these individual scalar types, you're going to be doing your for I equals, for j equals, those nested for loops corresponding to it. There are certain functions that exist in the C standard library that allow you to work with ranges of memory at a time. That sometimes can be a better choice than even for just this example, copying element by element A into B. Part of the challenge is until you know that that function exists and remember the name of that function, there's a discoverability issue. I'm telling you there's a function that does this, but if you didn't know it, then how would you know to look up that function and find it? But for example, for copying one region of memory to another region of memory, there exists a function in the C standard library that does exactly that. It is called memcopy. And we tend to want to use, if they exist, standard library functions, as opposed to kind of re-implementing them ourselves as we go, even for something as simple as copying one array to another array. A couple of reasons. It's a very standard approach to use a built-in library in the language. It's presumably going to be more efficient, and it's just going to be easier to review, to debug, to work with that code later on. The challenge then, of course, is using someone else's code versus using your own code. That's always the trade-off. Do I just write it myself, or do I trust somebody else's code and try to understand somebody else's code? This function is called memcopy. For me, when I want to work with a new function, I like to kind of copy in first the function prototype or the description of what that function is doing, just to have it handy. That page, of which you can find the manual listing for all of these C standard library functions, does say exactly what the function does, but it's written in that kind of data sheet style that everything it says is technically 100% correct, but it's almost like a foreign language, and you have to kind of convert the formalisms in this type of data sheet document to what does that mean in practice? What does that mean for me as a programmer? For this particular listing, the parameters is a pretty good way to understand it. Destination is the pointer to the object to copy to. Source is the pointer to the object to copy from. Count is the number of bytes to copy. So it takes as input destination, a source, and a number of bytes to copy. Why does it do destination first and source second? Why isn't it source first and destination second? I don't know. You just got to go look at the definition and make sure if you get it backwards, then you try it again and you swap them around. That's all I can tell you for that. But in this case, what's the name of our destination location for this example code? We're copying A to B. So which one, between A and B, which one's our destination? It's B. Source then is A. The final tricky thing about this and a large number of other functions in the C standard library, this count parameter, again, the documentation did say it, but you have to kind of read it and like narrow in on very specific words that may not mean that much to you at the time you see it. Count is the number of bytes to copy. We have B, we have A. Do we know how many bytes we need to copy? How many bytes do we need to copy for this example? The answer is all of them. We need to copy all of the bytes of A to all bytes of B, but there is no all. We have to tell it exactly how many bytes are we copying. Do we have any thoughts? How would we get to that number? We would absolutely have to use num rows and num columns. Other thoughts along those lines? How would we use them? Good start. Num rows times num columns, which I think I left it at 5 and 10, right? That's 50. What does that give you in English? What does num rows times num columns give you for this problem? Yeah, it gives you, the dimensions of the matrix, it gives you num rows times num columns, the total number of what? Total number of numbers, or using the variable type, total number of ints in that array, right? 5 times 10, there's 50 ints in the array. It would be nice if this function took in the total number of ints, but it doesn't. It takes in the total number of bytes. If we know we have 50 ints, how do we calculate how many bytes do we require? This is going back to like week 2 of the semester. That's correct. And there's a built-in that tells us exactly what that is. Do we know what it's called? It's been a while since we've used it. We're going to start using it more. There's a built-in in the C language syntactically that tells us for a variable type how many bytes it is. Doesn't really matter, you don't remember it, because now you know it. Size of. Give me the size of int. You could also have done size of A would also have worked, or size of A of 0 for a given element. For this array, I need that many rows times that many columns times that many bytes per element. That should return back 200, which is the number of bytes we want to copy. And it's not going to be that exciting, the output, because it's going to be the same result as we did it before. And, you know, I think you can debate which version of this array copy code is better. You know, there's different parameters to consider here. This is nice and clean because it is very understandable. This is a built-in standard library that presumably is very well written, very well optimized, and just a nice piece of code. Both generally can be assumed to work on any platform you're running C programs on, so there's no portability issue. It depends. I guess it depends on what else you're doing with your program. But this is your general workhorse for copying blocks of memory around in your system. You can always write a loop to do it instead, but now it's just one line of code. 1 versus, 3 lines of code, not that huge of a difference, but that's the trade-off we're exploring with that example. Sure. Yep. You give it a destination address, which is what that little symbol is implying in void star destination, a source address, and a number of bytes you want to copy, and it just copies from one location to the next. So let's try to put all that together with what we know so far about arrays and loops. And I'd like you to try to follow this example pretty closely today in class. I think for some of you, this will be very straightforward and obvious now, and for others, this will seem like, you know, black magic that we're doing here. We had this example a few weeks ago now, right? Where we had defined 5 variables, var1 through var5, and what we did was just a series of pairwise comparisons. Compare v1 to v2, swap them if need be, then v2 to v3, swap them if need be, all the way through. And we actually did that 5 times to get our entire array from a randomly sorted order to ultimately a completely sorted order at the end of the day. I still have that code here. We can bring it up here. The thought is now that with the 2 things we've added in the last week and a half, 2 weeks or so, where we can loop through, we don't have to kind of copy and paste the code every single time we want to do this. We have for loops. And now with arrays, we can have a much more generalizable, appropriate version of this same bubble sort code that really only worked for us for 5 numbers before. Now it should work basically for an arbitrary amount of numbers for us with the usage of arrays and then with the usage of for loops to process those arrays. So we're going to refactor that code. But this is back from where we were a few weeks back. We had a printf, scanf for 5 values, and then we had this basic kind of swapping code, right? Check if one was greater than the other. If so, have a little temp to store that intermediate result and swap the 2 results, swap v1 and v2. And if you look at the rest of the code, we just kept kind of doing it over and over again, just kind of copying those values all the way through. Well, to refactor it, I think we'll start and just kind of delete most of this code to begin with, because we don't really need most of it. It's going to kind of delete it so we have a better starting point here. Now we know if we have a program for which we want to have 5 integer values that we're going to be sorting out, how should we declare that? v1 through v5 kind of worked. What's the appropriate way now to do it? With what we've learned, let's make an array. V is not the world's best name of an array, but oh, there we go. We're going to call it V because that was v1 through v5. And for now, because again, we're still doing this kind of static allocation, this compile time sizing of our arrays for the next few weeks still, we'll use that n to kind of encode in our program how big that array is going to be. Again, with the hope that if our code works for n equals 5, we then try n equals 50 and n equals 5 million, and it still should hopefully work at the end of the day. So instead of v1 through v5, we now have this size v array here. The other challenge I would say for this is that instead of a bunch of scanf commands where it's an arbitrary size, we could have a for loop where you're typing in every single value in your array. That will work for 5. It'll be very painful for 50. Instead, let's do what we did with the array copy example, in which we just initialized it to some random range. I'm going to copy this code. It's not going to be exactly right, but we should be able to refactor it for our purposes. This is initialization of array A for rand values in the range -10 to 10. Okay, it's no longer array A, now array V for rand values in the range, and let's do -n to n because we're going to be sorting them. We need an appropriate range for the sorting that looks good. For int I equals 0, I is not less than num rows. I should be less than what for this code? Help me out, friends. Say it out loud. N, just n. Single loop. We don't have a double loop because there's just a single value, single dimension of our array here. It's v of I. It's unhappy about not finding rand. That's technically defined in standard lib.h. So it should be happy now. Rand, this gave me a value in the range -10 to 10. So first it gave me a value in the range 0 to 20, and then it subtracted 10 from it. If I want -n to n, how would I change this code then?
Apply the same process applied to 10 by multiplying 2 times n and adding 1.
And then subtract n from it. That should give us a random value in the range of -n to n. It's not that big of a deal, but that's all we're doing with that. So we start with the value in the range 0 to 2n inclusive. We just subtract n from that value. That gives us -n to n. Again, because here we're sorting values, if we kept it in the range of -10 to 10, it wouldn't look very good. It'd be a whole bunch of ties, right? There'd be a lot of copies of -10, -9, -8. So we give it a larger dynamic range here. We should probably, what did that code look like? You know, before sorting, right? So before sorting, vals are We have our nice looking prompt here. And for our size n array, we are always doing that I equals 0, I less than n loop. We don't really know how big to do it, so we'll just do that, %d. And we want to print out that value of I. And if we want to have it look really nice at the end, no, that should be fine. We'll keep that extra spurious comma at the end that I didn't really like. All right, fine. We'll get rid of it. And then we'll close it. Print that last value separately from the rest, so you get the new line and all that at the very end. And because that code is probably okay for printing, let's put it afterwards as well. And even though our code doesn't do anything yet, we'll probably test it now. Generated 5 values. They should be in the range -5 to 5. Seems okay. And just quick sanity check, we changed it from 5 to 50. Seems okay. We haven't done any sorting yet, but at least we're printing the values out twice. And for testing purposes, less is more, because we want to be able to print it out and really understand and maybe trace it step by step. Okay. So we had code, and this visualization may be the best way of looking at it, right? We had code that for each iteration through basically determined what the highest value was remaining. Is it between the first two? Swap them if need be. Is it between the next two? Swap them if need be. Next two, swap them. Finally, we get to the last one, swap them if need be. The end result of that full iteration through is this last one is in the exact right location it needs to be. We found the largest one. Then we should do it again. We have found the largest one, run the whole thing again. We should have now the second to largest one, and then the third to largest one. We need to do it until we have everything in its appropriate place. For size n, how many comparisons do we have here? For one column of that set. Close. For size n, which n is 5 here. Okay, for 5, for sorting 5 numbers, for this first pass that gets us one value in the right location, how many comparisons and potential swaps do we have to make? 4. I guess it's not necessarily obvious that that's the case, but that's for size 5. For size n, we probably have to make n-1 comparisons here to get us started. Let's write it. I'm going to call it j, because this is going to be an inner loop eventually. So we want to do n-1 things, just like we have in that previous loop. J is less than n-1, j++. This version of the code is checking if v1 is greater than v2. What is the equivalent of that code for our array now? I want to check v1 versus v2, and then v2 versus v3, then v3 versus v4. What would that look like for our array now? So it's if. Let's do this first. It's if, then there's going to be temp equals something, something, something equal. We can almost like write the code, except we got to figure out what needs to go in those spots, right? We have to use our array. So we have j as our iterator through the array. We want to first start by comparing what? The first element in that array to the next element in the array. And this is using something we haven't touched upon that much yet. When we're at j equals 0, what is that element in the array then? It's the first element. We could hard code it. We could do v of 0 is greater than v of 1. We could. V of j, if it's greater than what? Absolutely. That's the first element, and that's the element next to it. That's v1 compared to v2 when j equals 0. And then we get through the loop, and then it's J1, J equals 1, then it's V2 versus V3, then V3 V versus V4. You do have to be a little careful. We have V of J plus 1, and we can probably finish the equivalent of that code here, right? It's the same as below, just using that array syntax versus that scalar variable syntax we have here. Now that we have this, both in the if statement and later on when we're using it, gotta be a little careful. Our code's fine here, but in general, you have to be a little bit careful. When you have I equals 0, I less than n, V of I is always going to be a valid reference, assuming your array is also of size I. Now that we have V of J plus 1, we got to kind of look back. As soon as you see J plus 1 or J plus 2 or J times J or something that's not just J inside your subscript for your array, you just got to double think back and say, did I just create a bug here? Basically is what you have to ask yourself. Because if I had just by default, as we've been doing for our arrays, had our for loop iterate from I equal or J equals 0, J less than n, then that would technically be a bug. And why would it be a bug? Because when we would get to J equal to n minus 1 at the very end of our iteration, this would be comparing V of n minus 1 to V of n minus 1 plus 1 to V of n minus 1 to V of n. And V of n is not a valid subscript in that array of size n. Only 0 to n minus 1. It would access past the end of the array, which, at least with Replit, has been initializing everything to 0. It would wind up swapping a 0 into our array that doesn't actually belong inside that array. So that would be a proper bug leading to an incorrect result. We kind of avoided that bug by recognizing that we only need 4 comparisons when n equals 5. We didn't need to do them all anyway. And it's for the same reason. It's not an accident that happened. 1 versus 2, 2 versus 3, 3 versus 4, 4 versus 5. There's no 5 versus 6 we have to compare. So there's just one fewer comparison because we're doing these pairwise comparisons. When we run that, inner loop, if we want to call it that, gets one element into the correct final position. We should be able to see that for this random code. 1, 5, 1, negative 3, negative 4, and the 5 does get into the right location. How many times do we have to run this then? So this was J minus 1, we called it. Or N minus 1, we ran this, right? N minus 1. How many times do we have to run it? Yep. N minus 1 times also for kind of the same reason. We get this one in location, these 2 in location, these 3 in location. You can think of this as only being these 4 in the right location. But if these 4 are in the right location, then the last one's also in the right location. So also N minus 1 times. So we have this inner loop that puts one thing in the right location, and then this outer loop that reruns it n minus 1 time. This is going to be a little different than our array copy example, because now for this outer loop, there is no ij of the array, right? It's still just a single dimensional array. This outer loop is just saying, do that whole pairwise comparison, just do it n minus 1 times. So we just need our for loop in this case to just repeat the operation that many times. My recommendation, select, when you know this is now going to be an inner loop, I selected it all, I hit tab, that indents it so everything's kind of in the right location there. This should work. There just happens to be a tie for 2 values were the same there, but yeah, that looks like that's correct, that's sorting for us. Technically now, this is a pretty minor optimization. We run this n minus 1 time. The first time through, we have to do all n minus 1 comparisons. Second time through, we only have to do n minus 2. We don't actually need to do this comparison because we know they're in relative order, right? Then n minus 2, then n minus 3, then n minus 4, etc. So this is more of an optimization because the code does look like it's correct, look like it is correct already. It was already n minus 1 comparisons. It's actually n minus I minus 1 comparisons. We don't really need to keep comparing to the very end each time. Only at the very beginning, and then there's one fewer value we have to compare each time. This is pretty classical bubble sort. It should still work for n equals 5. And then now we can try it for n equals 50. And we kind of stare at it to confirm that it is working correctly. And it appears to be sorting reasonably correctly. Try n equals 5,000. And it looks like we have a nicely, sorted array. You can't really tell. You have to kind of inspect it manually, but, it ends in 5,000. I bet if I scroll back, it probably starts at negative 5,000. It doesn't look tremendous, I understand. Yeah, I'm sure it's sorted. Yeah, okay. Roughly negative 5,000 is the first value. Negative 4,998 is the first one that got randomly selected here. It can actually then be very useful to then analyze this and say, how fast is this code that we've written for doing this sorting? And the problem when profiling the performance of your programs is for a lot of the programs we write, even though it doesn't feel like that should be the case, the time it takes to print your data is actually much larger than the time to do your computation. Printf, although it doesn't seem like that bad of a function, it's actually a very complicated function. And getting the results of printf into this kind of console terminal window is actually a pretty slow thing. For historic reasons, that's just something we have to be aware of. So if we want to do a performance profile of this example, what I would suggest doing would be to just comment out anything that's doing printing. That's one way to do it. There's other ways in which we can insert the timing code directly into the program. See if it actually works. That seems awfully fast. Profiling for performance is not a straightforward thing because there's a lot of variables slightly outside of our control here. What value is that? 500,000? Seems good and slow. Well, good. Let's try some value in between. This command is just the time command that says roughly how long does it take for whatever you provided as the next input to be processed. Let's do this a little bit more scientifically here. So if we started with, let's say 10. Okay. I'm just taking the make command that just builds it, putting a semicolon saying just do whatever's next, next command, and then time with the name of it. So that's n equals 10. Something a little wonky is going on then. I have broken this poor computer. What did I do? It is chugging along here. Let's see. I might have messed something up. Let's give it a second here. All right. I don't know what happened. Let's try it again. Fine. Let's try to be a little scientific here. So for n equals 10, 0.04 seconds. We'll then do n equals 100. That doesn't shock me. It's kind of a rounding error at that point, that type of runtime. N equals 1,000. Okay, we'll keep collecting data. If we can. Questions about this example as we wait for it to reboot. I'm just trying to collect some data for how long it takes to run. I commented out the print statements because I think the printing out 10,000 values would be significantly longer than the time it takes to do a sorting of 10,000 values. And in the process, we happen to break Replit. Okay, now we get some real numbers here. That's 10,000. I mean, for n equals 10 or even 100, that's a very small amount of code. 100,000, we know it chokes after a little while here. And there's things you can do as opposed to just waiting at a blank screen for something to print out or having too much print information. We could write this program such that, you know, every 1,000 iterations it prints out something or it prints out some status information because it doesn't look super responsive right now. Um, it appears to still be running. We'll give it a couple more seconds. Sorting 100,000 elements should not be that slow. So if I'm on, I don't know, let's do every 10,000. It did finish. That was 100,000. That seems really slow. I'm skeptical. Let's run it again. I don't believe that number. Oh no, it's pretty slow. Look at that. Not gonna have the patience to wait till 100,000 again because it's gonna be roughly a minute if we wait that long. But anyway, that's kind of a, you're running something, it's running for a long time. You don't want to necessarily be, deluged with all this printf that you can't really analyze anyway because it's going too quickly. All I added here to the code was every 10,000 iterations. Let's confirm that it's not stuck, that it's actually doing something every 10,000 iterations. That technically slows it down a little bit because you're adding a little bit of code, but a pretty small amount of code. We got a slightly different number there, but still the same order of magnitude runtime the second time around. When you're benchmarking software, it's a little tricky. This is a cloud computing environment that's being shared amongst lots of other people spinning up projects and doing code in parallel, all sorts of other tasks running at the same time. If you get the same order of magnitude performance, that's generally the best you can hope for, unless you lock down that system a lot more than what we would have access to here. But given that data, let me try to plot it. Don't know why we don't have it installed. Try to plot it. It's there, okay. Set output. Set output. Set terminal PNG, is that the command? And then just plot data.dat. Plot data.dat. That looks awful. Let's try that again. I mean, it's technically correct. That's kind of GNU plot for you. Plot data.dat with what are some of the ones we use, like line connectors? Let's see, connected lines. No, with what is that called? GNU plot connected lines with lines is fine. Line points, that's what it's called, not connected lines. At least it's connected there. And you start to get a feel for the approximate runtime of this. Let's get one more data point in there. And this should be a little bit quicker now because it's just 50,000. Okay. So when we talk about a particular algorithm, being quadratic in runtime. I could have added more data points. It doesn't look very quadratic because it's just, I could add more data points. I just don't feel like it now. And it's all kind of noisy data anyway. Or having the other term here is big O of n squared or order n squared runtime. As programmers, we can kind of just see it in our programs that we have this loop here, or this nested loop, that is of size n by roughly n by n. Meaning, for a given value of n, my program has to do n times n work, n squared work. And that becomes significant pretty quickly, right? This is just runtime in seconds here. When n was, 10, 50, 100,000, it didn't really matter. It was all just kind of, instantaneous runtime. But it grows quadratically. So as we get to n equals 100,000, which sorting 100,000 elements isn't really that large of a task, right? I mean, it's not nothing, but it's not this incredible, unfathomable type of task we have ahead of us. But when people say something is order n squared, that's literally what they mean. It can be modeled by a quadratic function. From the program's perspective that we've written, we have two double nested for loop of size n. So we're doing roughly order of n squared things, and our performance tends to then look like that. So as near the end of the semester, we're going to start to cover some semblance of different algorithms for doing things like sorting, and there's whole books, sections of the library on sorting algorithms. You will find that so much work has been spent on trying to improve upon that quadratic reality because we're constantly having to sort data for all sorts of purposes. From our perspective, for the most part this semester, we have something that works and we're happy. And if it's not fast enough, only then do we worry about how do we do some performance optimization. Lab 5, which I know has got a couple tricky parts to it, is the first assignment, I believe, this semester where one of the questions kind of expects you to look at the performance considerations. The monkeys typing. Has anyone gotten monkeys typing to work for finding words of length 7 yet? For finding words of length 2, 3, 4, 5, 6, you don't have to worry about optimization. For finding words of length 7, it's just awfully slow. And you may run out of patience, or Replit may crash in the process of waiting that long. You'll have to think a little bit more about optimization if you'd want to actually find matches of words of length 7. Because just statistically, there's just that much extra words to check against, and it just takes that much longer. But there's some aspects of how that problem is set up that call it for want of a better word, the doubly nested for loop approach to checking if there's a match or not. It works, it's technically correct, but there's a lot better way to do it if you want to more efficiently match whether a word of length 7 is found or not in the dictionary. I'll wait for people to come across that and have questions when they get to that point. For the purposes of sorting, again, there's whole books on the subject. We'll learn a few more sorting algorithms later this semester. Questions about any of this before we're going to kind of transition a little bit to our next topic? There may be. I'd have to check the spec. There's also limits to how many dimensions your arrays can have, but it's quite large, larger than you'd ever want to see inside your program. So, I've seen counterexamples, but anything more than 3 or 4 nested for loops is a sign you're probably not thinking about the problem quite right. Kind of for the same reason from a performance perspective. For a given value of n, this was n squared. Well, n cubed is going to be way worse, and n to the 4th even worse than that. And once you get to a certain value, well, you can kind of extrapolate it from there. You can figure out what this equation roughly is. That's n equals 100,000. What'll happen now with n equals million? How many, is it seconds? Is it minutes? Is it actually hours it would take for it to execute? There's just a limit to what value we have for having such deeply nested loops and deeply dimensional arrays as well. We'll start with this next topic, but it's pretty critical. So we won't start over on Wednesday, but there'll be that whole middle third of the class actually here on Wednesday. So it'll be it won't be new to you, but they'll have their minds blown on Wednesday. In some sense, we've been using arrays already. Before this topic was introduced with the topic of like integer or floating point arrays, every time we've been using something within the double quotes, that is also actually just defining a special type of array. You will hear the term string. You'll hear me use the term string. There is a string.h library. But for the most part, absent one or two small little implementation details, strings in C are not really a separate data type. They are just arrays of characters. Just like here we have our arrays of integers, you can also just define something to be an array of those char types, and that's what we refer to as a string. The reason we care a lot about strings is, well, twofold. First off, text processing is very important, right? So many of the programs we write have to do with processing input text, looking up things, checking things, just manipulating text. It's just a critical task. That's one half of the reason. Other half of the reason is because of the such common repeating operations we have with regards to text in our programs, there's a whole separate subset of the C standard library that provides effectively helper functions for working with these arrays of characters. But otherwise, and we'll talk on Wednesday about the other critical difference that can lead to some bugs along the way. Otherwise, when you're thinking strings, same as what we're already doing. We declare it as an array of type char. We do care about the length of that array quite a bit. It's just like we do for that integer array. And when we're processing it, there's some functions, kind of like memcopy, that do some of the grunt work for us. But otherwise, we iterate through the array of characters, and we do something on an element by element basis of that array of characters. I think it's an important enough topic that I don't want to like half start it right now. Let's leave things right here for today. And on Wednesday after the quiz, we'll pick right up and really dive into how to do arrays properly in C.